Welcome again to another CAN seminar. Today we have Professor Yong-Rak from Texas A&M giving a talk. So I'm gonna introduce Professor Kim. Dr. Yong-Rak is a Beavers Charitable Trust William F. Urban 41 Professor in the Zachary Department of Civil and Environmental Engineering at Texas A&M University. He received master's and PhD degrees from Texas A&M University in 1999 and 2003, respectively. Dr. Kim's research program is centered on materials engineering and mechanics for safer, durable, more sustainable, energy efficient, and environmentally friendly performance of infrastructure systems, including multiscale modeling and characterization, constitutive modeling of materials, viscoelasticity of solids, fracture, damage, and durability of materials. It's our huge pleasure to welcome Professor Kim here at Illinois. So let's give him welcome.
Thank you. Thank you so much. Okay, thank you. Good to go? Right. Well, it's great to be here. Thanks again for the invitation. This is my honor to be here with you, all of you, and thanks for coming. And I like to acknowledge, deep thanks to excellent professor, to Dr. Alkari, to Mueller, Hodge, and Young Fan, and then excellent group of here, ICT. So my big pleasure. So today I like to talk about some of my research, just the introduction, what I have done and what I'm heading to regarding transportation infrastructure based on the materials engineering, which is my primary area of research. So for just those of you don't know me well, just keep a quick intro about me for the last about 32, 33 years. So I'm originally from Korea, and my engineering degree in 1991 started. And then I went to Texas A&M for my graduate program in 1997. And then finished my PhD in 2003. I went to Nebraska as a faculty, junior faculty, started, enjoyed that quite a bit, and got back into A&M and right before COVID hit. So it's been about 4 years in A&M, enjoyed time there. And then here I am. This is first time visiting Urbana-Champaign, so it's great. So my research program is again about materials. Our theme is material fundamentals with sustainable infrastructure. So here you can see my website and my labs in Center for Infrastructure Renewal, CIR, and I'm in charge of materials manufacturing lab, AIMM, and nano micro characterization lab. And those are my research area. And some photos I can share, the lab there. So we do both experimental research and computational research to advance materials and transportation infrastructure in our group. So just quite busy, slides, but you can see we characterize materials in different aspects, mechanical characterization in different length scales, and microstructural characterization, and the chemical characterization, and information coming from those help our understanding and design of materials. And we also worked on the computational mechanics, modeling in multi-scale and multi-physics, and different length scales for different challenges. As you can see, just some snapshots. We are interested in fracture, nonlinear elastic behavior, and even smaller scale molecular dynamics modeling that we tried several years ago, and two-way coupled multiscaling that I'm going to talk about more today. So our target, as you are targeting, we are interested in resilient infrastructure systems and complex materials with heterogeneities in elasticity and anisotropy, nonlinear behavior, different kinds of stuff, as you can see some photos that we are working on. So how we do advancing materials and structures? My methods, my approach is multi-scale, multidisciplinary. So here is our ultimate like a structures for infrastructure systems. And depending on where we looked at, different length scales, I think we have different aspects to focus. Sometimes we are focusing on chemistry, sometimes we are focusing on physics, and the mechanics and others like data science is everybody talking about machine learning, AI. So for better civil engineering, construction, we want to integrate different knowledge, different information at different length scales. So that research methods can be applied to different applications. And I just list some of my research projects, for the past and today, and then heading to like roadway research, which is one of my major areas. And we're also working on cementitious mixtures for the construction, particularly like a low carbon, like a decarbonization, big theme for today. And then how we improve soil, again, the low carbon approach for civil military applications. And then we also worked on building materials for energy efficiency and geological repository to safely store the dangerous waste, like a nuclear waste. And energy storage, hydrogen storage in salt cavern, that's another project we are working on. And then, recent UTC let us work on the rail cracking. And some are more futuristic, maybe some of you are working on or interested in space construction through material science, materials engineering. So I'm gonna show mostly the first one, which is our primary interest, roadway research, modeling and mechanics of it. And then just one slide for each, just to give you just like a snapshot of what individuals are about. So regarding the sustainable roadways, again, the previous slide I shared, the multi-scale approach, multidisciplinary, can directly into this roadway problem. And I think a pavement problem, roadway problem is very good multi-scale problem. Again, depending on where we are looking at, what length scales, we are facing different challenges and different angles to investigate and then study. So it can be from very small scale molecular level, like somebody like you working on binder, and up to structural scale, meter, kilometer scale. So if we do like from smaller scale to the larger scale, it's more likely kind of prediction business. If we going from larger to smaller, it's more likely understanding of mechanisms associated to better design, better discover the materials. Sometimes we go back and forth, like two-way couple for the satisfying both ways. So regarding molecular level, which is not my area, I'm not a molecular dynamics guy, but one of my previous graduates were super interested in that, and he tried to model MD level for aged binder, like virgin binder, laboratory aged binder, and then field aged binder, and then did MD simulation for viscosity prediction. And then compare with like a millimeter scale DSR, and you can see huge mismatch, although we have pretty good rank order match up. So we found out, well, MD is a different world, and we can see in how it works out, what aging is associated. But because of different time scale, I think mostly time scale, like a nanosecond scale versus, just second scale, we have huge mismatch because the rate of shearing is very different. But that was finding we got. And then the other way, we did like atomic force microscopy. She's now more continuum level. So continuum level, the micromechanical modeling and prediction works very well compared to MD, which is not continuum level. So we could compare experimental and the computational, which is by finite element simulation for 3 different binders like virgin, aged, and rejuvenated. And the micromechanical modeling works generally good in that scale. So regarding micrometer to millimeter scale, which is kind of one of my PhD thesis topics, like DMA, dynamic mechanical analysis of sand asphalt matrix, or FAM. I mean, some of you are familiar with what I'm talking about. Fine aggregate matrix, and we try to develop the methodology that can characterize like a fatigue, cracking, and healing, and damage accumulation, and things like that from the binder level or matrix level. And you can see some experimental data nicely representing the behavior of material, like a viscoelasticity and damage evolution, things like that from this methodology. So it was pretty successful, from these efforts back in like early 2000 and later on. And then we also worked on like modeling of mixture. It's like a composite mechanics. You are familiar with that, I believe. So for a given mixture level, let's say asphalt concrete, you have like a particle, like rocks and, like a fan. And then when we characterize the particle property and the matrix property, let's say viscoelasticity, and we allow cracking of the matrix that we see from your testing. So we adopted like a model, like a cohesive zone fracture model to model the crack initiation and propagation, and then elasticity for the aggregate. So we combine all together, and then finite element modeling. I know some of you are very familiar with FEM and excellent efforts on that, and we could interestingly, we can simulate mechanical testing using this computer simulation. And here is like results coming up. So I'm talking about fracture. And the fracture is one of our primary challenges. And I think fracture cracking in solid mechanics is a very good topic to study. It's challenging. I would say it's very challenging. And we are interested in developing the fracture model to better understand and design the mix and structure in our transportation sector. So the model we adopted is like a cohesive zone modeling, which is nothing but extended crack tip, potential crack tip, where the separation resisted by the cohesive traction. So it's like a constitutive law for potential crack. So there are many cohesive zone models out there, depending on applications, materials, and their mechanical behavior. And the one we adopted, we used, is nonlinear viscoelastic cohesive zone model, initially developed by my colleague, long-term colleague, Dr. David Allen. And the good thing about this model is we have viscoelasticity, so that represent virgin material, entire process. We have a damage evolution law that simulate progression of the cracking. We have initiation criteria for crack initiation. we have termination criteria, length scale, and then cohesive zone strain lambda. So it's nice T delta relationship with other components coming together and contributing to the fracture initiation propagation nicely. In particular, regarding the alpha, so alpha is important part because alpha is actually simulating how damage progresses. And we know, materials like asphalt or bituminous material, the fracture is rate dependent. It's a viscoelastic fracture. So we try to represent better by using this Gaussian damage evolution function. That is very nice by having these three, like a set of, three single set of parameters account for the rate dependent fracture quite efficiently. So it's a really good efficiency. So as you can see, some validation study we did, different rates of, the pooling, like a testing, three parameters identified through calibration process works well. We can predict the, force loading time curve very nicely. So that's kind of brief overview of our fracture model. So with that fracture model, we can now apply to our civil engineering testing and application. Like SCCB, we do SCCB testing a lot. And then we can make our own finite element model. And then, provide right material properties, viscoelasticity, elasticity for rocks, and then cohesive zone fracture parameters we found from the calibration process. And then we can simulate using like a office computer instead of conducting the laboratory testing, like a virtual testing we can do with our computer package. And then as you can see, we can simulate a crack development through the sample. I think it's kind of realistic fracture. If you do testing, you can probably see like this way too. And then you see comparison between like aged group versus unaged group, high rep versus unaged, and model can capture damage process, entire process, like a testing we do in the laboratory. So modeling of mixture works. And then we can expand that mechanical modeling with multi-physics. Let's say different, conservation laws and natural laws, like conservation of the mass, like a diffusion process of water. Moisture damage is our primary problems, right? And for that, like a modeling of moisture damage, I think we need to link physics together, like diffusion process due to conservation of mass, and then mechanical cracking, conservation of momentum. So those two physics can come into together, coupled, either sequentially or two-way coupled. This is particularly sequential coupling. And the purpose of this paper, we published it several years ago, was to characterize the damage, how water affects damage progression in three different important parameters like stiffness and strength and energy. And that multi-physical modeling can simulate SCCB testing with water, different levels of conditioning, like no conditioning, 1 day, 2 weeks, and a month. And then from that model capability, we could identify how damage progress over concentration level. So it's kind of a mechanism characterization study through the computational modeling with multi-physics incorporated. And we can do the same job to see the effect of microstructure, like, what if we have air voids, which is true. What if we have, aggregate the matrix interaction more sensitive to water or not, like hydrophilic or hydrophobic? Let's say limestone is more hydrophobic phobic aggregate, and siliceous gravel is more hydrophilic aggregate. When we use different kinds of aggregates, then your fracture pattern will be very different, either like a cohesive or adhesive due to water penetration and the diffusion process. So the model can take care of that, effective factors. Okay, so far I talked about from a smaller scale to up to a mixture level, mechanical load, and then moisture damage. And now I like to talk a little bit about then either more challenging problem, say 3-4 length scale combined, let's say from micrometer to meter scale, like a crack scale, which is micro crack scale to a component level, maybe millimeter, and then mixture level, centimeter, and then pavement structure, like meter, even kilometer scale, right? So we have 3-4 major length scales. And how we can do this job? Well, same concept. We just need to link more scales, and then different physics and mechanics can come in. So in this job, the way we can do is like typical one-way couple upscaling process, which means we basically go from this direction to this direction, just one way, and the linking to this direction, like predicting the behavior of a larger scale. Or we can do even back and forth, like a two-way couple multiscaling. That will much better than just one-way linking in order to address the damage evolution, the effect of microstructure to pavement performance with the damage evolution, more realistic, observation based. And then the two-way couple multiscaling is really work better. So upscaling is we get the mixture property, and the property from mixture can be input of pavement structure simulation, like a cracking, like a top-down, bottom, or whatever cracking problem. Or we can do up and down looping process through homogenization of each time step, so that we can directly address microstructural change, evolution to pavement problem, which is true in this particular case because we're going to get cracks evolved. And then we're going to get some aggregate orientation, maybe some are changing over time too. So that microstructural change should be addressed. And also, the two-way couple multiscaling is beneficial in order to consider both mixture design and structural design together, because we consider small scale microstructure as part of the entire process. On the other hand, upscaling is limited. So upscaling, just snapshot, we do mechanical testing, like a dynamic modulus testing, SSCB, and we got results from laboratory testing. And then the properties out of there can be input of the structural modeling, such as you see different stage of load or movie right there, like a cyclic truck loads coming in and out. And then we have, contour plot nicely concentrated at the bottom of asphalt layer, as we know, and then potential crack initiated and propagated through the process. So this is good. I mean, this is maybe still very working well, but the things is like we need AC mixture testing to be done, which is time and labor intensive. And then this is the way we are not addressing mixture design and structural design at the same time, but they actually one body. I mean, we just separate the scales in two different ways, but it's a one body because your structure has mixture right there. So we want to consider mixture design and structural design together, and two-way couple multiscaling really works better in that sense. But one-way couple, again, still working very well. And we can see, kind of parametric analysis. What if I change truck load or truck speed or change the base material, like a softer granular base or stiffer concrete base under the asphalt layer, or thickness of AC, or property of AC, like using rejuvenators or polymer modifiers or wraps, different kinds of things coming in, then AC property can affect your pavement performance. As you can see, like percent damage as, as a function of a number of loading cycles. So we can see that. I mean, we can do good parametric analysis and effect of individual design variables. And we adopted that method into sort of a validation using the data from FHWA through the collaboration. Their, alpha, data, like here, this is their data from this testing. And then this is our simulation results from our computation. And we compare each other using the data, like a mixture data and the structural configuration with two mixture tests, dynamic modulus and SSCB. And we got, in general, pretty good agreement between the two. So I think one-way coupling still works very well. But like I said, about 2-3 minutes ago, this method is somewhat limited. I would say upscaling cannot accurately address the effect of mixture details, like heterogeneities, like aggregate gradation, binder properties, like component properties on pavement response and structural design. Because mixture properties, if you imagine, mixture properties in your structure are not same all the time. I mean, it varies. I mean, depending on where you are, like under the tire load versus far away from the loading zone, your mixture property over there will be different over time. So it's a spatially dependent and temporally dependent, both. It's time dependent and location dependent, and it evolves. Microstructure evolves. Structural property, layer property will be different from location to location over time. So how can we come up with the method to take care of these limitations we see from upscaling process? Maybe two-way coupled multiscaling the way. I mean, two-way coupled multiscaling links 3 length scales, like component, like aggregate and binder, and the mixture design, and then structure, pavement structure. We can directly link all together so that these two major limitations are accounted for. So let me just show you how it works. It's a concept demonstration. Suppose I have a pavement, like a 3-layer pavement, and this is initial condition. So this is like a location I just picked up. Looks like this. It's cartoon, right? And then this mixture property will be with this stiffness, like a modulus right there. And then I apply truck loads. And then right there, because of like a tension, we may develop a little micro cracks. And these micro cracks will make the location over there weaken. So your stiffness will be dropping. And that reduced stiffness should be the property for the next time step. Realistically, right? I mean, your property will not be same as before. It will be degraded because of damage. And that amount of degradation is different from here to there, right? Because of the loading condition and your boundary condition. And the next truck load came in, and then now we have more damage. And then your stiffness drop again. And that reduced stiffness should be input for the next time step. So in each time step, like a loading cycle, you need to account for this realistic evolution and change over and over and over. So like large scale to small scale, like a mixture and crack, and then small scale to large scale, it's like a looping. It's looped. That's why we call it two-way couple. And you notice the color right there is somewhat lighter gray, indicating kind of degraded location, property. And it continues like this. So we have to deal with that. And then like here, it's a demonstration slide. So I got 3-layer asphalt pavement, AC, base, and subgrade, and I just we multiscale many numbers of the elements with this like a representative volume element, and we looked at just two locations just for demo, top and the bottom, and we can apply truck cycles, and I don't know if you can see something going on at the bottom one. Hopefully you can see like a lot of small lines develop, like a initiation of cracks, like a fatigue. Let me play again. And then the top one is under most likely compression, right? We all know, I mean, this is a basic knowledge we all have, but it's a demo. Structure, mixture, talk together, real time, two-way couple, right? And as you can see, microstructure evolves over time. And that amount of change different from location here to any other location, right? Because you have different loading condition and the boundary condition. So this way will be very useful for design, both mixture and structure together, which is actually one body. So just some results we got by changing like a base layer type, or like here, granular base versus concrete base. The trend of the damage evolution is quite different depending on the stiffness of the underlying layer. This is a case with different microstructure, some coarse aggregate gradation versus final gradation, different levels of the damage. And then this table tells you how we can even optimize or select the mixture design, structural design for target performance by playing with your design variables. Let's say you can play with the thickness of layer, you can play with the property of a layer, you can play with both. And what will be the scenario you can target with maybe minimum amount of resources, like smaller money or resources. Then here, sort of similar pavement performance cracking, three different scenarios, like if I have 15 centimeter AC versus 10 centimeter AC, but by having 24% better fracture resistance of mixture, you probably get a similar performance. Then you now can think of what would be the better optimum scenario for your engineering. I mean, that can be studied. So here is a application again into the Federal Highway ARF study. We tested for just upscaling one-way couple. So here is a snapshot of entire figure, like from the mixture, let's say SSCB, we did it, and then we can find the SSCB fracture properties from this level of efforts. And that will be input for the two-way coupled multiscale scenario, where I got representative volume element directly from your SSCB sample, and then linked to a structure with this amount of global element. So here is a global scale. This is a local scale, including any crack development, if you wish, and that will be linked together in two-way couple. And then we can see different levels of progression of the damage, like 350 cycles to about 10,000 cycles, progressively growing damage, and at different locations of the loading cycles. And simply we just compare lane 6 and lane 7. It takes a lot of time for simulation, by the way. So two lane cases are 6 and 7, and here is the ALF data to be compared. And 7 worse than 6, and that was captured by ALF data too. So this indicates the kind of validity of the concept, but we still need some more validation to be done, and it's coming up. Okay, so quickly, the summary so far, I would say the way the multi-scale, multidisciplinary the approach, integrating different aspects, mechanical, chemical, microstructural, and the physical aspect help our understanding of our complex system. And in particular, two-way coupled multiscaling can account for various complexities like mixture heterogeneity, inelastic material behavior, maybe anisotropic behavior, damage evolution in realistic length and time scale, with significantly reduced testing computing efforts. What that means is, again, we only consider component materials, right? We don't really need to do mixture testing because component material properties will be input for mixture and structure in one shot. So that is really reducing a lot of efforts. Just component testing done. And I think this methodology integrated with multi-physics, even moisture damage or temperature, differential kind of thing can tackle, various challenges for today. I mean, we make mixture more complicated, and we also think about climate change, decarbonization, big theme, and I think that will help a lot. So far, it was about my roadway research. And but now just one slide for each for other things. I think the same concept, similar approach can be applied to different challenges, different problems. So here is a problem to develop like a cementitious or concrete mixtures with low carbon, like alkali activated materials like that. And we can do similarly like a multi-scale characterization. We can see mechanical aspect, microstructural aspect, and chemical componential analysis, and the knowledge coming into make your understanding better through the mapping process from different angles. Similarly, for the low carbon, again, alkali activated based soil stabilization. I know Professor Tutumiller does a lot of work, soil improvement, and we are now interested in like a chemical admixture stabilization, but we want to see what are the mechanisms behind, how much effect by using A versus B from the multi-scale aspect. In particular, we apply like a DMA into the soil research, which is one of my PhD students is working on. And then this is a quick slide on the energy efficient building materials using phase change materials, PCM. PCM is a material that change phase like from liquid to solid depending on temperature. And then it can absorb the latent heat and then dissipate the heat when the temperature changes. So it's an interesting material for energy efficient building construction, and it can save our energy bills. And then DOE is interested in kind of this approach. And here is a snapshot of one project we are working on, sponsored by US DOE, to store like a nuclear waste for a long time, let's say 100,000 years. If you think about nuclear waste, it should be safe storage. And the project is basically develop new buffering engineered barrier material that is under very interesting situation, like heat generation from the canister storing nuclear waste, and then surrounding rock provides like the water. So it's like a moisture temperature interaction of this yellow material, which is most like a bentonite, very stable clay. But we like to improve the property using inorganic microfibers to improve the properties of it, like a desiccation correcting like that. And some are futuristic research I'm interested in for civil engineering. I think civil engineering can do a great job on this space construction, more geotechnical and structural. And I'm working on developing construction materials for like a lunar and Martian condition without using water. So some of you are familiar with like a sintering, which is basically you heat the soil, the lunar soil, and then solidify it to develop a construction material. So this is kind of snapshot summarizing ISRU, in situ resource utilization space construction. So ISRU means we don't bring any material to the moon because it's really expensive. So what if we just use whatever available on space for the best? Okay, and then sintering could be one methodology we can think of. So you see, actually we can make nice hard products. And then this is a recent project we just started through Sandia National Lab, a DOE lab, for building the salt cavern to store the hydrogen. Hydrogen is important energy, right? And very explosive. And we want to store hydrogen safely underground with a salt dome. And then when the hydrogen coming out, in and out, then you have a lot of pressure, up and down. And then we like to understand how it behaves, like constitutive modeling, most likely viscoplastic, and then microstructural change. We can use like X-ray CT and different kinds of stuff to better develop model. So that's about the project. And then rail cracking, I talked with Errol before my presentation, and here is like rail cracks, right? I mean, you know that. I mean, rail buckles are like a summer, and the cracks more like a winter time, and because of thermal fatigue, since I'm working on fracture, maybe we can do simulation of the rail cracking such as like this. So when you build rail heads, I think there are some defects in there, and then the defects create cracks over cyclic train loads. And this is a sponsored project by USDOT, UTC Center of Rail we are working on. Okay, I think that's pretty much about it. Hopefully I could deliver what I do and what I'm interested in, and then heading to. My message will be, I think the mechanics is really contribute to our field. So far our civil engineering transportation infrastructure has been somewhat empirical, but we're heading to mechanics more and more. Professor Akari does a lot of work on that. I mean, many of you are working on, advanced modeling, and this is, I think, a part of the discussion today. So we're heading to that direction, and I'm also very interested in that direction, and that was my research. So my students, some of them already graduated, so the photo is not up to date by today, but that's what I have. And then my sponsors for the last about 20 years for my research program. Oh, just list of references for my presentation. If you are interested in, you can go in and then see any more details. So those are there. And the slides are shared with you, so you can use whatever. And that's it. I really appreciate your attention and
Thank you, Professor, for this excellent presentation. We'll open for questions now. Does anyone have any question for Professor Yong-Rak?
Yes.
Oh, okay. Thanks, Yong-Rak. Really great presentation. Fascinating work. So many different things over the years. So it's great to see it all compiled. One thing I was very interested in is the multi-physics model with the moisture combined with mechanical damage. Did you look at ever the effect of when that water freezes and kind of becomes another solid in the expansion and propagating damage, maybe effect of that?
No, not yet. The model I showed you is before that, wet and dry, not free thaw. That's another challenge because now we're talking about volume change, phase change, liquid solid. Challenging, right?
Very challenging.
Yeah, very challenging.
So much interest in that one.
But
yeah,
we can talk about it. I mean,
Definitely.
I think that's a direction for the future. Now I think we can model wet and dry, but free thaw is the reality. We need to do that. And I'm super interested in, maybe this is actually great even NSF type research efforts, but I don't know, NSF are really fascinated by supporting like asphalt.
Yeah,
not so much, but maybe Federal Highway US DOT is interested. Yeah, we can talk about that. Yes.
Thank you so much for a nice work. But I was curious if you could share with us what is the computational effort for the one-way coupling, how long it took versus two-way? And then if I may, so I think you nicely link between the different scales, but I was curious, what does relative damage mean at the end of the day in terms of like years to failure or number of cycles to failure? And particularly what are your thoughts in adding another scale, which is now in temporal? Because spatial you did, now adding that temporal scale of cycling seasons, and so forth.
Okay, so your first question is about computational efforts between one-way coupling versus two-way coupling. One-way coupling, you only need one homogenization. So you do model mixture and then get the property, homogenize it, and that will be input for your structure. So it's a homo problem. You finish mixture simulation and then just for the structural simulation, and they're separated. It's one way just feeding the input to the next level. Computationally, is everybody does. I mean, basically you get the mixture simulation and then you do structural simulation. Two-way coupling, you do homogenization every time step, because at time step 0.1 second, you get the mixture simulation, you homogenize the mixture, the property goes back to your structure. The next time step, you got change in your mixture, you homogenize again, and then go back to structure. So it's keep homogenizing over and over and over and again. And depending on how many elements in your global scale is linked to local RV, that's computational efforts. If you just simulate one or two elements that you are interested in, it's easy, not very computing efforts. But if you really want to know everywhere, I mean, no matter where they are, it's a parallelization of computing. So it's a computational efforts is huge. Yeah. And your second question was about relative damage and temporal.
Scale. So now you nicely change it when there's cyclic loading, but I'm interested when you're farther, when their season changes.
Oh, then you need to have multi-physics coming in. So that two-way couple multiscaling is a multi-scale modeling, two-way couple without multi-scale and multi-physics. But now we're talking about temperature seasonal change. It's a multi-physics. So then the computational power will be exponentially growing, because you are now talking about every moment your temperature change up and down. And so now I think you need to then make your own scope. How long you want to work on it. And then let's say, I don't think it's possible with our computing power for today, like a simulation of a few years, realistically varying, changes of temperature and moisture, everything together. It's not there yet. It's very limited. It's still very limited. So computationally, it's intensive. Yeah, great question, Andeli. Yes, Professor Akari.
Thank you so much. We really appreciate your visit with us today and
Thank you.
all the great work that you have been doing over the years. But definitely there is one thing that attracted my attention, which I was very pleased to see it, especially that I'm very familiar with the ALF sections that you did. We did some experimental work on them, and that worked really well with the IFIT test, and we were able to predict. But my question to you is, when you did the modeling, giving the variation of the materials that they have warm mix, they have RAB, they have RAS, they have everything. So what did you do for the modeling? You just changed the properties of the binder after you test the materials, like extract, or what did you do?
No, we got their SSCB data.
Okay.
So let's say lane 6 SSCB mixture A, right. Lane 7 B, we got their data. We calibrate the data of SSCB results.
Okay.
So it's a mixture data calibration, fracture property of mixture level. And then that mixture data went into structural simulation for pavement. Yeah, that's a one-way couple.
So you did it for the picture that you provided.
Yes.
Okay, that makes sense.
Yeah, they're mixture data.
Yes.
Yes.
Absolutely.
Yes.
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 Yeah, that was exciting to see that you were able to simulate that because it was very complex.
Right. So we didn't consider their like additives and makeup. We just consider just mixture itself and then get the properties out of it. Fracture properties, by the way, and the viscoelastic properties. And those are just input for the pavement simulation.
Yeah.
Just for the rank order comparison, just to see if a model works, in general.
I was asking a question, so I can encourage the students to ask. Nobody's asking any questions. You really.
I know your intention. Yes, Errol.
Really very much enjoyed your presentation, excellent presentation. And I was also impressed with all the details that you got into in terms of talking about multi-physics and all kinds of, especially on the damage. One thing I didn't notice though, are you taking into account moving wheel load effects when you do a cycle?
No, it's a 2D. So it's not like a realistic 3D, back and forth. It's like a cyclic.
Typical moving wheel loads bring the rotating stress fields.
Yes, yes. We're not, cohesive zone modeling is not very good at 3D simulation of cracks yet. We can still do it, but computationally, it's not a joke. So we do a 2D. I think 2D still gives a lot of information. So it's a game. What is like your accuracy versus efficiency, and where is the sweet spot? So we adopted, well, because of limitation of cohesive zone model in 3D, particularly viscoelasticity. Why don't we just simplify problem in 2D and then get the output from there? So yeah, it's a great question, Errol. It's not moving wheel load.
Right.
So, yeah.
Okay, it's time now. So let's again thank you, Professor Yong-Rak.